はい。 All right, it's 5:30. Let's go ahead and get started. All right, good afternoon, everyone. Good evening. Great crowd today. How's everyone doing today? Good, good. All right, last class before spring break. I know it's probably the hardest class to get to and get through. So we'll just go ahead and get through it. But after this, we have a week off, which is good. Except for those of you taking the comprehensive exam tomorrow. So in that case, you're probably sweating bullets right now. So best of luck on that as well. Okay, so the plan for today is we're going to continue on with our lecture notes on finite element forms. I'm hoping we can finish it just so that, when we come back from the spring break, we can kind of start with we can kind of get rolling for the midterm exam, because the next midterm exam is rolling around soon. And it's going to be based on all this stuff here. Okay. All right. Not really much in the way of announcements. Remember, ANSYS Activity 2 with the programming components, that's going to be due next Tuesday. So it's going to be due during the break. So make sure you get that done before. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So when we left off on Tuesday, we were talking about this idea of finite element forms, right? So we've kind of started this journey. It started last week of taking differential equations, and we want to see how we can turn these differential equations into finite element problems, right? And by finite element problems, I mean problems that involve a matrix, element stiffness matrices, assembly, boundary conditions. Kind of the same process that we've already followed for the direct stiffness method, but applied to differential equations. Okay? And so the very last thing that we went over last time was that, we went through all these derivations, we took the weak form, we applied a linear shape function to it, and we ended up with an expression for our element stiffness matrix. Okay. So this is our element stiffness matrix for 1D problems. Okay. So our element stiffness matrix, KE, is equal to integral from x1 to x2. And we have a vector multiplication on the inside. So first thing we have here is a column vector, dn1 dx, dn2 dx, multiplied by e times a, multiplied by a row vector, dn1 dx, dn2 dx, all integrated by dx. Okay. Question. All right, so this was our expression for the element stiffness matrix. This was kind of the very last thing that we did on Tuesday. Okay. And so the way you get a matrix from this is that you multiply that column vector and row vector together, because the column vector is a 2x1 matrix essentially, and a row vector is a 1x2. Okay. And so if you multiply these two together, you end up with a 2x2 matrix. Okay. More often than not, if you're using linear shape functions, then all the entries in the matrix are going to be constant, and the only thing you're integrating is just e times a. Okay. But we'll do an example of that in a bit. Okay. So that's what we obtained from the left-hand side of the equation. So you kind of recall the way we got here was that we took our weak form, we did our integration by parts, we plugged in our weighting function, and we plugged in our representation for a solution. This is what we got. Okay. Now let's do the same thing, but for the other terms in our weak form. Okay. And so if you recall, there are two other terms that we have to evaluate, right? We have one term involving the body force, and then another term involving the Neumann boundary conditions. Okay. And so both of these combined will form something called the element forcing vector, which is a relatively new concept. And so we didn't really do much with these in direct stiffness, but you'll kind of see the role that they play here. Okay. So let's start with the first term. So the first term was the integral from x1 to x2 of our weighting function, w of x, multiplied by our body force term, b of x, dx. Okay. Where w of x here, remember, this is our weighting function. Okay. And b of x here, in this case, represents a body force. Okay. So of course, we're going to plug in for both of these. The body force is a term that's problem dependent, and so we can't at this time because we're doing a derivation, we can't plug in for that. Okay, but we will plug in for that for a problem. Okay, for our weighting function, we're going to plug in our shape function representation, because what we said was w of x is equal to w1 and 1 of x plus w2 and 2 of x. Okay. And remember, when we have our representation in this form, we can put it in vector format. Okay. And so what we can say is this is a row vector of coefficients, w1, w2. Okay. And then we have a column vector of our shape function, n1 of x and 2 of x. Okay. Okay, so let's go ahead and plug that in. Okay. And what you'll see is that there's not much we can do beyond this because we don't know what b of x is at this point. Okay, or we're leaving it general to b of x. Okay, the one thing I will do though is that because w1, w2, those are constants, I'm going to factor those out of the integral. Okay, and so what I get from this is w1, w2, factored out of the integral from 0 or from x1 to x2, excuse me. Okay, then we have our column vector here, n1 of x and 2 of x multiplied by b of x dx. Okay, and that's as far as we can take it for this term. Okay. So when we get to an example problem, you'll see that once we do have something we can plug in for b of x, we'll know what our shape functions look like as well, n1 and 2. And so all this term would be we're just plugging in here and then we're just evaluating. Okay. And this term will become part of our element forcing vector, which you'll see what role that plays once we kind of get to the example. Okay. All right. Any questions on this so far? Okay. All right. So this is good. All right. So the last term that we had in our weak form was actually a boundary condition term. And so it looked like this. And so we had W multiplied by A multiplied by the surface traction T bar. Okay. And this is evaluated at the Neumann boundary. So this is X is equal to X T. Okay. All right. So this term here is really special. So compared to the previous two expressions, right? So if you look at the element stiffness matrix and the body force term, those two terms or those two integrals are evaluated at every single element. Okay. In contrast, this term right here is only evaluated for elements that border the Neumann boundary. So in reality, for most 1D problems, at most, you're just gonna have one Neumann boundary condition, if at all. So, for all of our 1D problems, at least to start with, this means that this term is only gonna show up for just at most one element. Okay? So you're not gonna evaluate this on most terms, okay? Or more on most elements, okay? It's only gonna be one. Now, of course, this is going to change once we get to 2D problems. So in 2D problems, you may have, multiple elements that are bordering a Neumann boundary condition, but, we'll cross that bridge when we get there. Okay, so just like we did with the body force term, we're just going to plug in for our weighting function. Okay. And so we're going to use the exact same expression that we had up here. Okay. We have W1, W2, a vector, and then N1, N2 vector, right? And so this term here then becomes W1, W2 coefficients multiplied by N1, N2, which are functions of X. Okay. Multiplied by A, E bar. Okay. But the caveat here is that everywhere that we see X, we're going to evaluate it at the Neumann boundary. Okay. Okay. And so putting those things together, our, our body force term here, as well as our Neumann boundary condition term, both of these things combined, or their sum, comprise our element forcing vector. Okay. So our element forcing vector is Fe, okay? And it has two main contributions. It's going to be integral from x1 to x2 of n1 of x and 2 of x multiplied by b of x dx plus n1 and 2 of x times a times t bar, but only evaluated at the Neumann boundary condition. Okay. And so if you look at all the terms here, everything is just kind of a 2x1 vector, essentially, right? We have some extra steps along the way. We have some integration that we have to do, but essentially we just end up with a 2x1. Okay. Okay. So now that we have our element stiffness matrix and we have our element forcing vector, we can put together the full linear system that represents this particular element. Okay. Okay. So our element stiffness matrix, Ke, this is multiplied by our solution vector d bar on the element is equal to Fe. So exactly the same as we did before. Okay. So what you're going to see is that, in the example that we're about to do, we're gonna be following a very similar process to our direct stiffness, methodology. The only difference is going to be in how we form the element stiffness matrix. Okay. The other thing that's going to be different is that when we do assembly, right? So when we go to assemble our global linear system, not only are we going to be assembling the element stiffness matrices, but we're going to be assembling these element forcing vectors as well. Okay. Previously, the only way that we modified our global forcing vector was when we applied boundary conditions. Okay. But now, because we have this body force term and we have this, a different way to apply our Neumann boundary conditions, our loads, that's going to factor into that as well. Okay. So what you're going to see is that it's a very similar process. The main thing that's going to change is just how we compute the element stiffness matrices. But hopefully, this next example is going to be very familiar to you guys, with the exception of some of the integral stuff. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's go ahead and do an example. Okay. So let's say that we're going to do a 1D elasticity example. We have our wall here. We have a rod. Okay. And so the rod is going to be fixed to the wall at x is equal to 0. Okay. The total length of the bar is 20 meters. We have a body force, and so that's going to be new compared to what we've seen before. For our body force, B of x, we're just going to assume it's going to be constant, so it's going to be 2 newtons per meter. Okay. And at the end of the rod, we're going to have a fixed amount of force, of pressure. Okay. So we're going to have a T bar of -5 Pascal. Okay. So what we want to do is we want to compute a finite element solution for the deformations in this rod. And we're going to use the following discretization. And so the mesh for this problem is going to be given to us. Okay. All right. So here is our rod here. Okay. We're going to go with the 2-element system here. So we're going to have one element that spans from x1 is equal to 0 to x2 is equal to 5. Okay. So our first element is going to be fairly small. And then our third node here, x3 is going to be at the end of the rod. At x3 is equal to 20 meters. Okay. Okay, so we have 2 elements, element 1 and element 2. Okay. Oh, we need the properties as well. So we're going to assume our Young's modulus E is 5 kilopascal. Okay. And one thing that we haven't seen in direct stiffness is that our area, or our cross-sectional area for the rod, is going to be changing as we go along the rod. Okay. So our area is going to be a function of x is equal to 1 plus x squared divided by 400. Okay. So this is a problem that we previously couldn't do with our direct stiffness because of the presence of the body force term and because our area here is going to be changing as a function of x as well. Okay. All right, so there's a lot going on, but I picked this problem just to kind of show you, kind of the everything that you can do with this new framework. Okay. All right, any questions on just the setup for the problem? Okay. All right, so let's go ahead and get solved. So, even though we are in kind of a different setting here, our process is still going to be the same. So just like we did with direct stiffness, our first step is to compute the element stiffness matrices of both the elements. Okay. But in addition to the element stiffness matrices, we're also going to be computing the element forcing vectors as well. Okay. All right, so let's start with element 1. And so our element stiffness matrix in this case, oh, and I forgot to mention, we are assuming linear elements, and so our shape functions are linear. Okay. And so the general expression for the element stiffness matrix is x1 to x2 dn1 dx dn2 dx multiplied by e times a dn1 dx dn2 dx dx. Okay. Okay. So okay, let's go ahead and plug in all the entries for this vector here. Okay. First, let's note the endpoints. Okay. So what are we integrating between? And so if we look at element 1 here, right? The x value for the left node is given by 0. Okay. And the x coordinate for the right node is given by 5. Okay. So if x1 is equal to 0, x2 is equal to 5. Okay. Next thing we need are the shape function derivatives. Okay. So dn1 dx, we computed that expression last time. So based on the linear shape function, we know that dn1 dx is going to be 1 divided by x1 minus x2. Okay. We know what x1 and x2 in this case is. x1 is 0, x2 is 5. And so we plug those in. dn1 dx is minus 1 over 5. Okay. Meanwhile, dn2 dx is 1 divided by x2 minus x1, which is the reverse of that. And we plug in x2 and x1 into that, we get 1/5. Okay. All right. The other thing we know is that we know E, right? The problem tells us that the Young's modulus is uniform all throughout the rod. So the Young's modulus here is 5 kilopascal. 5 kilopascal is the same thing as 5,000 Pascal. Okay. And then our A of x is a function 1 plus x squared over 400. All right. So that's a lot to plug in. So let's go ahead and just kind of plug it in kind of step by step, and so we can kind of see the whole process. Okay. Okay, so plugging in, we get integral. Let's plug in for x1, x2. So that's going to be integral from 0 to 5. Then we have the vector dn1 dx and dn2 dx. And so that's going to be a minus 1/5, then a positive 1/5. Okay. E times A, E is 5,000. So let's plug in for that. Okay. Times A is 1, the function 1 plus x squared over 400. Okay. Then we're going to multiply this by another vector, which is dn1 dx, dn2 dx. So we have a minus 1/5, positive 1/5 dx. Okay. Okay. So everything that's a constant here, I'm going to factor out. I'm also going to perform that vector-vector multiplication. Okay. So that 5,000 is a constant. I'm going to pull that out. Everything in the vectors here are constant as well. So I'm going to pull all of those things out. Okay. And so if we do that, we get 5,000. Okay. Times our vector. So I'm just going to do vector-vector multiplication here. So we're going to end up with a minus 1/5 multiplied by minus 1/5. Okay. Then we have minus 1/5 multiplied by a positive 1/5. Okay. Then we have positive 1/5 multiplied by a negative 1/5. And then positive 1/5 multiplied by positive 1/5. Okay. But all those are constant, so we don't need to actually integrate that. So we're going to integrate from 0 to 5 of 1 plus x squared divided by 400 dx. Okay. Okay. All right, so we have some arithmetic to do. So on the matrix, we have 1/5, we have a bunch of 1/5 times 1/5, and so that's gonna be 1/25. Let's go ahead and multiply the 5,000 by that. So every term in that matrix there is going to be 1/25, either positive or negative. So the diagonal terms are positive and the off diagonal terms are negative. If we multiply 5,000 by it, so that 5,000 would multiply by every single entry in that matrix. So 5,000 divided by 25 is 200. Okay. And so on the outside there, we have 200 minus 200 minus 200, 200. Okay. Then after that, we have the integral of a relatively simple polynomial. So let's go ahead and take the integral of this. And so this would be x plus x cubed divided by 1200. Okay. And we're going to evaluate this between x is equal to 0 and x is equal to 5. Okay. All right. So unfortunately, plug in for those integration bounds because we have the divide by 1200 there. We don't get a very nice number. So I'm going to just go ahead and do that arithmetic for you. But essentially, this is just going to be another constant that we're going to multiply by every entry in the vector here. Okay. Okay. So if we do that, we get 1020.83 minus 1020.83 minus 1020.83 and positive 1020. Okay, so that there is our element stiffness matrix for element 1. Okay, so a little bit of a different process, and so and this one I went kind of particularly slow just so you can kind of see all of the steps of the arithmetic and the integration. And so doing the element stiffness matrices for these types of problems, it takes a little bit more work. I think it's a little bit less annoying just because there's if you compare this to a frame element 6x6 matrix with all those different terms. I think this is a lot easier, but you do have to do some integration and you do have to do a little bit of kind of linear algebra to get here. All right, any questions on just this part of the problem here? Okay. All right, so before we move on to element 2, let's go ahead and compute our element forcing vector for element 1.